Hello everybody, my name is Ethan. Welcome back to the machine learning course on Codecademy. In today's video, we are going to be bringing it together. So we have done over 30 videos to this point, and we are about 95 to 97% of the way through the course. It looks like we have building machine learning pipelines, and that's about it. It's been a long time coming. I'm pretty happy on the progress that we have made. This is actually my third video today. I want to try and get it done, see if we can get onto some project that I want to do. I have a couple ideas that I really want to do. We'll see how that works. Okay, so let's just get right into it. Bringing it all together. Welcome to the Building Machine Learning Pipelines. You're now ready to combine your machine learning knowledge with software engineering skills to build machine learning pipelines with scikit-learn. Why learn building machine learning pipelines? Machine learning applications are powered by robust end-to-end pipelines. Building these pipelines involves combining the ability to build and tune high-performing machine learning models, as well as writing production quality code that can fit well within a tech company's engineering workflow. So what are we going to cover in this module? In this module, we'll learn about the different components of a machine learning workflow and how to turn your workflows into end-to-end pipelines. Along the way, you'll learn some nifty scikit-learn tools that will help modularize your machine learning code to make it reproducible and effective. Prerequisites. This model requires prior knowledge of the machine learning as well as basic software engineering in Python. Go check out our intermediate machine learning skill path and our software engineering for data sciences skill path to brush up on either. Learning is social. Whatever you're working on, be sure to connect with the Codecademy community in the forums. Remember to check in with the community regularly, including for things like asking for code reviews on your project work and providing code reviews to others in the projects category, which can help to reinforce what you have learned. All right, machine learning workflows. There are many steps in the process of creating, implementing, and iterating over a machine learning model for a specific data-driven problem. While there is no single universal way of sequencing the different steps that go into a workflow, there are some general principles that are good to follow for optimal performance of a machine learning algorithm. This article will lay out the steps of a machine learning workflow and how to implement them for any data set. A note to the learner, this article and module requires intermediate level knowledge of machine learning. Obviously, that's what we've been doing, so let's get into it. Machine learning workflow. A machine learning workflow has the following steps. Depending on the data set, the question we're trying to answer, and the tech stack we're working with, one or more of these steps can be omitted or combined together. The steps are 1, ETL, extract, transform, and load data. Number 2 is data cleaning. Number 3 is train, test, validation, split. EDA is exploratory data analysis. Number 5 is feature engineering, normalization, removing autocorrelations, discretization. I'm probably saying that word wrong. Model selection and implementation. Step 7 would be model evaluation. 8 is hyperparameter tuning. 9 is model validation. And number 10 is build machine learning pipeline. We're not going to go through each of these steps in detail. So number 1 is extract, transform, and load ETL data. ETL, right? This process can look different depending on the data sources and the tech stack you might be working with at a specific company, but it's often the case that data is stored in an SQL database with a cloud service provider like AWS, DigitalOcean, etc. Depending on the volume of data, an engineer would use a tool like PySpark to extract this, transform it, and load it into a local database. Sometimes this falls within the purview of a machine learning engineer, but depending on the technical sophistication of the stack, there might be a data engineer or pipeline engineer performing this task instead. Data cleaning and aggregation. This step is often combined with the previous ones. This can involve a range of tasks depending on the form and type of data, as well as the problem the machine learning pipeline is being designed to solve. Some examples include dealing with null or missing entries, confirming timestamps to a standard carrying out to a standard, carrying out aggregations like grouping events based on timestamps by the hour or day, and grouping IPs by location, etc. Since Spark is best suited to perform such tasks on big data, this task might very well be the transform part of the aforementioned ETL step. Alternatively, raw data might get handed over to the MLE, who then does the same after the ETL step. Train, test, validation, split. The next step before editing the data in any manner is to perform the train, test, validation, split. You're very likely familiar with the idea of training and testing data and MASH. Scikit-learn's model selection module has a train, test, split function that has used to do this. If you've ever implemented a machine learning model using scikit-learn, you've likely followed or written the piece of code, xtrain, xtest, and obviously within this course, we've done that a lot of times. In the above example, we see that the test data makes up a third of the original data set. The random state argument is set there to ensure reproducibility here, i.e. if we used 42 again, it would split the certain data set in the exact same manner. The training data set is used to learn a model's parameters, and then test data is used to test its performance. For models in production, there's a third portion of the data set that's set aside known as a holdout or validation data set used to tune hyperparameters and or to perform model validation later on. If you'd like to revisit the train, test, validation split, check out this article. I don't think we necessarily need to do that, so we can continue on here. The reason we don't want to perform data manipulations before splitting the data set into training, test, and validation data sets is that we don't want data points from one of these to influence the other. Suppose we needed a machine learning model to predict housing prices and we wanted to standardize a feature like the size of an apartment. The average of this would look a little different between the entire data set and each of the individual data sets. Scaling the entire column to the average misses the unique information contained within the subpopulations and will make the model evaluation and validation process less objective. All right. Number 4, exploratory data analysis. Exploratory data analysis, or EDA, in the context of a machine learning workflow is the step of inspecting, analyzing, and altering your data to get it ready for machine learning modeling. Often, this is the step where decisions on how to deal with outliers, transform are made. Our EDA and Python course covers this topic exhaustively, but specifically the articles performing EDA before supervised classification, regression, or unsupervised learning are worth checking out if you'd like a refresher. Feature engineering. Feature engineering refers to an umbrella of methods to prep, select, reduce features in a machine learning problem. This can involve methods that overlap with EDA, such as normalization, removing autocorrelations. I guess I should look up this word and how to pronounce it. It's not going to tell me how to say it. Merriam-Webster. Discretization. Discrete. Okay, we're wasting time here. Whatever. Feature engineering can also involve using machine learning algorithms like PCA to reduce dimensionality, or methods that are implemented during model fitting step like regularization. If you'd like to brush up on feature engineering, the feature engineering skill path is for you. Model selection and implementation. Now that we're ready to test out machine learning models, the choice of the model depends on the attributes of the data one's working with, as well as the type of question we're trying to answer. Scikit-learn has a nifty cheat sheet to choose the right estimator. And file not found. That's just so amazing. Okay. Model evaluation. Now we're getting to the iterative part of the workflow. Whatever model is built, it must be evaluated on the test data for classification problems. Metrics like accuracy, precision, recall, F1 score, and OROC scores indicate how performant the model is. For regression problems, scores like RMSE and R-squared are commonly used metrics. If you'd like to review these ideas, check out this lesson on evaluation metrics. Machine learning engineers iterate over different types of models to figure out the most optimal model for the problem at hand. Hyperparameter tuning. Once a model has been decided upon, it can be tuned for better performance. Hyperparameter tuning is essential in making sure that the model does not overfit or underfit the data. If you'd like a refresher on what hyperparameters are and methods of tuning hyperparameters, the hyperparameter tuning module might just be for you. Model validation. Model validation is the process of making sure the model is still performant on data that it hasn't seen at all. Neither in the training phase nor the testing phase. This can be done either during the hyperparameter tuning step or after. Typically, the same metrics used during the model evaluation phase need to be used here as well as to make a reasonable comparison with the former. Finally, number 10, build the machine learning pipeline. When a machine learning workflow is a part of a production cycle, it's often the case that a model is tuned and updated based on incoming information. In other words, the model that worked well on last month's data might not be applicable for this month. It is the job of a machine learning engineer or pipeline engineer to make sure that the model deployed into production is thus flexible, alterable, without affecting the rest of the code base. Machine learning pipelines allow one to do the same. A machine learning pipeline is a modular sequence of objects that codifies and automates a machine learning workflow to make it efficient, reproducible, and generalizable. Summary, we've gone through each step. We're ready to build a machine learning workflow and turn them into pipelines. Very cool. That's interesting. Data engineering is not over 150 XP. Come on. All right. Here we go. Maybe not. Okay. From workflows to pipelines. In this lesson, we're going to learn how to turn a machine learning workflow into a pipeline using scikit-learn. A machine learning pipeline is a modular sequence of objects that codifies and automates a machine learning workflow to make it efficient, reproducible, and generalizable. While the process of building a pipeline is not singular, there are some tools that are universally used to do this. The most acceptable of these is scikit-learn's pipeline object, which allows us to chain together the different steps that go into a machine learning workflow. Turning a workflow into a pipeline has many other advantages too. Pipelines provide consistency. The same steps will always be applied in the same order under the same conditions. They are also very concise and can streamline your code. The pipeline object within scikit-learn has consistent methods used to use the many other estimators and transformers we have already covered in our machine learning curriculum. It is usually the starting point for a machine learning engineer before turning to more sophisticated tools for scaling pipelines such as PySpark, and we will delve deeper into this later in this lesson. What can go into a pipeline? For any of the intermediate steps, it must both have a .fit and a .transform method. This includes preprocessing, imputation, feature selection, and dimensionality reduction. The final step must have the .fit method. Examples of tasks we've already seen that could benefit from a pipeline include scaling data, filling in missing values, and one-hot encoding categorical variables. All right, data cleaning. To introduce pipelines, let's look at a common set of data cleaning / EDA tasks dealing with missing values and scaling numeric variables. We're going to convert an existing code's base that performs these tasks to more concise code that uses scikit-learn's pipeline using the following steps. First, to define a pipeline, we pass a list of tuples of the form name, transform / estimator into a pipeline object. For example, if we wanted to perform imputation with a simple imputer first and scale our numerical variables with a standard scaler next, the code would look as follows. So we would import firstly pipeline, set the pipeline object, and then we would quickly basically do a tuple with the name of imputer, simple imputer, and then scale with a standard scaler. Perfect. Once a pipeline object has been instantiated, the methods .fit and .transform can be called like we would with any other data transformation object in scikit-learn. So we would then do a train test split, and then we would fit it to the X training data and transform the pipeline using the testing data. If the pipeline includes a machine learning model as well, .predict can also be called down the line. Each step in the pipeline will be fit in the order provided. Further parameters can be passed to each step as well. For example, if we want to pass the parameter with mean equal false to the standard scalar, we would simply add it within the standard scalar call in the tuple there. All right, in the code editor, we've loaded in a data set from the UCI machine learning repository containing information about different attributes of abalons, which looks like kind of like a clam, I guess. Maybe like what are those things that hold pearls? Shells, just like a shellfish kind of deal. Typically used to predict the age of the abalone. We've defined the predictor and target variables, identified the numerical and categorical columns, added some missing values to impute, and performed a train test split. So first we're going to examine the existing code that fills in missing values with the mean value using a simple imputer, and then scales the data using a standard scalar. Rewrite this code to create a pipeline object using the same code given the narrative. So, as it says, we want to rewrite the way we were doing it using a pipeline object. So what we'll do is we'll call a pipeline object pipeline, make sure that it has all been imported. Yes, it has, right? I'm not going to ask an AI about the code. And then what it wants us to do, again, is pass in two different tuples in a list. So we have a list here, or an array. We'll have our first tuple. It does want an imputer using a simple imputer. So we'll say imputer, and then we'll put in simple imputer. And then we'll get out of that tuple and create a second tuple called scale, and we will use a standard scalar and using standard scalar, rewrite this code. Right now that looks about good. I don't think we need to put in the with mean equals false, just because I don't think I see it anywhere here. So let's run that, see what happens. Expected. Oh, I put pipline instead of pipeline. Let's actually do pipeline instead of pipline. And now we want to fit the pipeline to the numerical columns on the training data, transform the test data, numerical columns only, using the fit pipeline, and call this object xTransform. So first what it wants me to do is fit it, so we can do pipeline, not pipline, pipeline.fit using the x training data. Then it wants me to transform it and call that object xTransform, and we're setting that equal to pipeline.transform, and we're going to pass through the x testing data. And we want to next, cannot use mean strategy, non-numeric data, could not convert string to, am I doing this wrong? I didn't think I was doing this wrong. And methods with xtrain, replace xtrain and xtest in .fit with xtrain and number columns. So you want to add the index of num calls. We can do that. Num calls. It wants me to use instead. Let's see why it might want me to use that data. If we go to num calls, it selects all of the columns that have that are NumPy numbers. So, or I guess that means number columns. Is that what it asked? Fill the pipeline to the numerical columns of the training data. So, yep, it did say that, and I just didn't read it. All right, let's see. To see if xTransform and xTest fill missing scale are equal, use the NumPy array equal function. The array will be 2 arguments inside this function. Then save the results to the variable array diff. If the arrays are equal, then returns true. Okay, so it wants me to verify pipeline transform test set is the same. So we'll say array diff is equal, and then we'll also print array diff. But then we'll set up array diff here by saying np.array equal, and I assume we pass in two different arrays here, x underscore transform, and then we'll probably also do it with test fill missing scale. So it printed out true, which means they are equal, which is good. And now we want to define a new pipeline median, with the imputer strategy parameter set to median. So we can, I assume, keep the other one the same. We'll call this one pipeline underscore median. Set that equal to a pipeline object with the value of, oops, come on. We want the value, I would assume, of imputer changed this time to be, instead of simple imputer, we'll just do median. And then we'll hop outside this tuple. And instead, I would assume we still use the same tuple of scale, just because it doesn't specify if we do or not. I'm just going to include it with the standard scalar. So we have created that, and we can run that now. Median is not defined. Median. Let's view the solution really quick and see what is happening. This time we put strategy. Oh, I see. With the imputer. Okay, so we would just add, that's my bad here. So we would keep our simple imputer, and instead pass in the strategy equal to median, and see how that ends up working out for us. To compare the results between the two pipelines, implement the following steps. Number one, fit the numerical training data with the pipeline median and transform the numerical test data to obtain a new array X transform median. So we can compare the first two by fitting the pipeline median one. So first we'll fit it using pipeline median. And again, it does say, I did pay attention this time, that it does say numerical training data. So we will want to use the same thing that we did here using pipeline median, dot fit, using the X training data and only the numeric columns, right? And then we can also do set a new variable called X transform median and set that equal to pipeline median dot transform. And again, we're going to take the X testing data at only the numeric columns. So we now want to calculate, I'm going to give myself a little bit of space here. Usually like to have it not all the way at the bottom there. To compare the results between the two pipelines, implement the following steps. We did step one. Now in step two, we're going to create a new array diff. So we'll say new array diff is equal to the sum of the absolute differences between the two arrays. So it would be similar to array diff that we did before, but instead we're kind of wanting a number between the two arrays. So what we'll do is we'll do absolute value of we'll do X transform and subtract X transform median, And then we'll wrap this in a parentheses and do a dot sum. Hopefully that works. I think that would end up working here. We'll see if that ends up being the case. It is the case. Awesome. Feel pretty great about that. We can now print out new array diff, and we'll end up seeing that the difference in the two arrays is about 35.8, somewhere around that range. Okay, cleaning data categorical. We're now going to implement a task similar to the previous exercise with pipeline.pipeline, but with categorical variables now. Specifically, we'll be dealing with the missing values in categorical data and one hot encoding categorical variables. Oh my gosh, guys, I'm absolutely itchy right now. It feels like there's like a cobweb on me. We'll do that. Specifically, we'll be dealing with missing values in categorical data and one hot encoding in categorical variables. We will convert an existing code base to a pipeline like in the previous exercise. The two steps in detail are simple imputer will be used again to fill missing values in the pipeline, but this time the strategy parameter will be needed to be updated to most frequent. One hot encoder will be used as a second step in the pipeline. The default setting in scikit-learn's one hot encoder is that a sparse array will be returned from this transform, so we will use sparse equals false to return a full array. All right, so examine the code. And that fills in the missing values with the mode of the categorical variable. And we'll create a new pipeline object named pipeline that will do the same task by first, making in the pipeline is a simple imputer that employs the most frequent strategy. And the second step is a pipeline called one hot encoder with the arguments drop equal first and sparse equal false. So we'll create this pipeline called pipeline, set it equal to a pipeline object with the values of first imputer, and we're going to set that equal to the simple imputer. And inside simple imputer, we want to use the most frequent strategy, so we'll specify that strategy is equal to most frequent. Okay, in the second tuple that we will create, we will first say, would it be encoder perhaps? That is a good question. I am going to just quick check the solution to see if it's just encoder. Most frequent, OHE. So it's just OHE, not OHE. And then we'll put the one hot encoder with the drop argument being set equal to first and the sparse argument being set equal to false. So that should work. Too many values to unpack, expected 2. Interesting. Let's actually look at the solution one more time, see if this isn't exactly what they wanted from us. Not tools, sorry. Let's go to the get unstuck here. Okay, so in ours, the only difference is the fact that they put sparse first and then drop equal first second. Basically, when we do something like this, it's going to mean that, well, let's see. I'm a little concerned now because this looks fairly similar, and I don't know if... Okay, pipeline is equal to pipeline with the imputer set as simple imputer with strategy equal to most frequent. Next would be OHE, one hot encoder with drop equal first and then sparse. I will just change it to see if this ends up doing something. We'll get rid of sparse equals false and instead put it right here, right? So sparse equals false, and then drop would be second. Looks like it's doing the same thing here. if I just completely rewrite, I'll just copy and paste this and see what happens. I'm not going to fill because that would fill all the answers, right? What happens now? I'm really curious to what I got wrong. Please let me know in the comment section below what I got wrong there. I don't necessarily see it right now, so just let me know. All right, first fit this pipeline to the training data with the categorical columns alone. So again, it's specifying this time just the categorical. Last time we had the numerical columns. This time it's just going to be the categorical columns. And we can do that by using cat columns. We can index it with xtrain equals cat columns, saved as cat columns. Next, transform the data and call the resulting array xtransform. So we did this very similarly. First, we'll do pipeline.fit using the x training data, but only going to be using the cat columns or categorical columns. Then we'll save a new variable called xtransform, and we're going to save that equal to pipeline.transform, and we are going to transform that testing data using the categorical columns only once again. So now that we've done that, we've called the resulting array xtransform. We're now going to see if xtransform and xtestFis are equal. So we can do that using that numpy function. We're going to set it equal to the variable check arrays, set it equal to np.array equal and inside that we will first put xtransform, and the second value will be xtestFill missing 1. Okay, and now we'll print out the value of check arrays. Remember that when we actually print it out, it should xtestFill missing OHE, not 1, OHE. One hot encoder is what it's standing for there. That is my fault. Nice, we got that one right. All right, column transformer. Oftentimes you may want to not simply apply every function to all columns. If our columns are of different types, we may only want to apply certain parts of the pipeline to a subset of columns. This is what we saw with the previous two exercises. One set of transformations are applied to a numeric columns, other to the categorical ones. We can use scikit-learn's column transformer as one way of combining these processes together. Column transformer takes in a list of tuples of the form name, pipeline, columns. The transformer can be anything with a .fit and .transform method like we used previously with the simple imputer or simple scalar, but it can also itself be a pipeline, and we'll use this in the exercise. Following what we did in the previous example, we're going to create two pipelines, one for the numerical preprocessing and the other for the categorical preprocessing. First, create a numerical preprocessing pipeline, numValues pipeline that has a simple imputer named imputer with strategy set to mean and a standard scalar named scale. Okay. So we're going to first create the numVals. So numVals is equal to a pipeline object with the first tuple being the imputer, and the imputer is a simple imputer, if I can spell today. And did we want anything inside that simple imputer? Yes, we did. We wanted our strategy set equal to mean. In the second one now, we will create another tuple, this time with the scalar. We're going to set that equal to the standard scalar. It could actually, I think it's only scale, so we'll do that instead. In the standard scalar, we want nothing, just everything kind of default there. This should be correct. Too many values to unpack. See, we got the same thing here. Oh, it's because I think this might be the exact reason why I don't have a second one that ends off that invalid syntax now, though. I think now we can actually get rid of one. Yes, so I kind of kept editing code. That's probably what happened in the previous example as well. So I kind of figured that one out. And yeah, it ended up getting a check mark now. All right, now we're going to create a pipeline for categorical variables and pre-processing called cat vals. This pipeline should have column transformer. Okay, so I'm going to create it up here at 1, but it's going to be called cat vals, and it's going to be a new pipeline with this. Once again, we're going to again set the imputer, and this one's going to be another simple imputer with the value of strategy set equal to most frequent. Now I should have set that equal. Oh, see, I did the same thing. So now that should be good. I see where I was actually getting it wrong now. So next one is going to be OHE with the value of 1 hot encoder with arguments sparse equal to false and drop equal to first. So that's the second pipeline. Similar to the sample code in the narrative, create a column transformer named pre-processes that takes in the 2 pipelines that we've defined as transformers and then names them num preprocess and cat preprocess respectively. So again, let's kind of look at the syntax. First, we're going to create we want to call it preprocess, and again, it's going to be the column transformer. And if we go up above, it looks like we have first a keyword transformers that ends up becoming a list of tuples. And in the tuple, we want the name, the pipeline, and then the columns. So makes sense. So first we'll call it transformer. I believe it was just it was transformers. And we have the list here. And we can open that list up and now put in the tuples, where first tuple will be the name of the processes. We'll start with the num. So we'll call this one num preprocess. Second value was the pipeline. In this case, we want to use, since it's a number, we're going to use num vals. And then the last one is the columns, right? So we can use num vals. And in the second one, we can create another tuple here called cat preprocess and set that with cat vals. Oh, let's actually see. I put num vals twice, and now I'm not 100% happy with what it was. It's actually, sorry, this should be num calls. Sorry. So now we can do cat vals and cat calls. Perfect. So that should be good. Tuple object is not callable. Let's see if they did it the same, or do I have it backwards? So they have preprocess is equal to column transformers is equal to, and then they opened it up. If I were to is that not how they have it? I didn't put a comma after my second or my first tuple, so I think that should work now. Unexpected keyword trends and foamers. Okay. Transformers. We're fixing all the bugs right away here, making it easy on ourselves today, apparently. I am ending a FaceTime call really quick. I'm going to text them really quick. Making video. 1 sec. Okay, fit the transformer on the training set, transform the data, and store the transform data as xtransform. Okay, so fit the transformer on the training set. So now what we can do is preprocess.fit on xtrain. And store it as, and then we can do xtransform as equal to, xtransform is equal to preprocess.transform with the value of x test. Perfect. I think that's all that. All right, I think I'm gonna kind of split this video up. So this is going to be the end of this video. This is going to be part 1 of machine learning pipelines. If you did enjoy this video, please be sure to give it a like, subscribe, and I'll see you in the next one. Peace out.